Recording in progress.
No, it should be fine.
Good morning and welcome everyone. So now we are heading toward the second last day of the CIMPA school and the second last lecture of Kaie Kubjas. Over to you, lecture number 3, Kaie Kubjas.
Thank you. So today we won't talk about non-negative matrix factorizations. So we will basically prepare for tomorrow's lecture. So we will talk about real algebraic geometry. Actually, we will start with algebraic geometry. So this might be a reminder for many of you. I would like to start with a, let's say, thought experiment for you. And actually, you can already, the people in Lahore can already see a partial answer to what I'm going to write. So the kind of question that we are interested in today and tomorrow is consider the map given by two polynomials. So phi from R2 to R2 that maps UV to 1/2 U plus U times V and 1/2 V minus U cubed. Okay, and the question that I'm going to ask you is, what is the image under phi of the unit ball E? So the unit ball in R2. So all the elements UV such that U squared plus V squared is less or equal than 1. So, and question to you, how would you approach this problem? Like, you know, I think the problem is clear to everyone. It's very easy to state, but how would you answer this?
Maybe look at the boundary.
Look at the boundary. This is what I would usually do first, because maybe boundaries will help. How would you look at the boundary? Like, how would you determine the boundary?
Think about it.
So I think one more relation will be use that relation U square plus V square is equal to 1 in the above and drop it to 1. So just maybe by using parameterization.
Using parameterization of the boundary of the unit ball. Yeah, that's a very good idea. I haven't thought about this.
Let's say to the I theta, then yeah.
Yeah. And then so these both suggestions go in like the direction of looking at the boundary, right? Any other suggestions before I'm going to give you 3 suggestions how to answer this problem. Okay, so if not, then so the first idea. Now let me also share the screen. So the very first idea, and let me make it larger. This idea actually comes from Pablo Parilla. is to sample points in the unit ball. So you can see the first picture over here. So there are like, I think in this case, maybe 100, no, actually 10,000 sample points. So this is Mathematica code. So the sample points are these black points. And then for each sample point, you apply this map that's written on the board. Okay, and then you get this image over here. And the points on the boundary, these are blue. The points in the interior are black. So you can see actually, yeah, so you can see image over here. And the boundary maps like the different points over here. But very interesting phenomenon, in my opinion, is that if you look the boundary of the image over here, then it actually doesn't come from the boundary of the unit ball. So if you look like this part of the boundary of this image here, so this is not blue.
Yes.
So meaning that it doesn't come from the boundary of the unit ball, but it comes because there is this folding, right?
Yeah. Due to cubic equation?
Well, the folding, it doesn't have, so I will answer it, but it's not only due to the cubic equation. So the folding can basically, or maybe it is, I'm not sure if the folding can happen. No, even like, let's say, if you think of the example of a real line and the map x squared, then also folding happens at 0, right?
Yeah.
So it doesn't, basically, if you have a linear map, then folding can't happen. But if you have anything that's not linear, then folding can happen, right? So what I'm trying to say here, it's really important to somehow realize that, at least to me, wasn't obvious when we started this project in 2016, that, you know, there are these boundaries that don't come from the boundaries of your pre-image. Okay, so this is one approach, but of course, you know, we are mathematicians. Maybe we are not completely happy with this approach because, you know, we get a nice picture, but still, yeah, this doesn't give us so good answer. Another approach, unfortunately, it's a little bit small, and I'm not sure how to make it larger. Let's see. The command plus is going to work. Unfortunately not. So another thing, there is resolve command in Mathematica. So from algebraic geometry, maybe some of you are familiar with elimination. And but now we don't have algebraic varieties, although I'm going to define them. So like I'm rushing a little bit ahead, but here we have inequalities. So we are in the world of real algebraic geometry. And in real algebra, so what we have basically, we have this parameters, u and v, and then we have a map to r squared, maybe where we denote our coordinates by x and y. And then we want to eliminate this u and v and keep x and y. And so this is called quantifier elimination. And in Mathematica, there is this command resolve that does quantifier elimination. And you can see for this particular example, it gives like this very, very long answer. So it's like some combination of equations and inequalities. But I have to warn you, you know, you can't do much larger examples than this example, right? And you can then region plot now draws what this resolve command has found here. And now you can see the picture of the image. So there is some similarity what you saw here, but now it's really like there are polynomial equations and inequalities that are used here. And then a third option, and this goes to these boundaries that we already mentioned. So let me again, so this is from a paper called How to Flatten a Soccer Ball, where we study this question, you know, what are the images of, so let's say it's a case study. And here you can see another figure. And actually the boundary is a subset of two irreducible curves. So one curve is this curve that comes from the boundary of the unit ball. And then there is this other curve that's where the folding happens. Okay. And this can be now computed completely using tools from algebraic geometry. So if you're familiar with Macaulay 2 or like maybe Singular, then you can draw this irreducible or like find these irreducible curves using this computer algebra software. And actually the curves are they're given by these two polynomials. So one is degree 3 and one is degree 6 polynomial. And this degree 6 polynomial is the image of the unit circle. So it defines the image of the unit circle. So this red curve here corresponds to a degree 6 polynomial, this polynomial Q.
So how did we reach to these two polynomials?
Okay, so so this is not for this example, but has the same idea. Yes, but for some reason I can't make anything larger.
No, it is readable.
Okay. And what happens? So F and G are the two polynomials that we're interested. So in our case, it would be 1/2 U plus UV. And then we have to, so we have variables U and V for our parameters, and X and Y are for the coordinates in this image space. Okay. And then we construct the idea of the parameterization. So this is this idea X minus F and Y minus G. Okay. And then we take the Jacobian of this idea. And so, and then we, the idea that we're interested in will be the, where the Jacobian, the maximum minors, not maximum minors, in this case, I guess it's 2 times 2 minors of the Jacobian vanish, right? So it's where the Jacobian drops rank. And this is the locus where the implicit function theorem doesn't hold. The implicit function theorem says if you have like some implicit functions, you know, we can we can explicitly express the function. But for this, we need that the Jacobian of our parameterization has full rank. Right? So this is how the polynomial P is constructed. So we can talk about it later during the tutorial more if you want. And then for the boundary, so we construct the polynomial H that defines the boundary. And then now we take this polynomial for the boundary together with the parameterization map. So the idea I, that was the idea X minus F and Y minus G. And now we consider where the Jacobian now we consider where the Jacobian of this ideal drops rank. So the main ingredient somehow is considering the Jacobian either for the parameterization map or the parameterization map together with the boundary. Okay, and then we need to do the elimination. Sorry, there are many things going on here, so I'm not expecting that you know, you can follow, but we can go over this like carefully during the tutorial if you want. But this is like, let's say, the algebraic geometric approach to find the boundaries. But then going from the boundaries to actually finding the image, like the inequalities, that's still non-trivial matter.
Command plus sign?
I tried. This is what I usually do, and it's not working.
Can you try the other way? Go to Finder and see show view options. That's one.
And which one from here?
And it should say text size.
Oh yeah.
See this.
I think only for the Finder.
So, are you using Safari or Python?
It's Safari, but I think I'm done basically now with let's say showing pictures, and I can try to figure out how to show them larger during the tutorial. So if you want to discuss this part again, but the main idea, what I wanted to show, like, you know, it's such a simple question, but I think the answer is like, it's non-trivial, right? And there are many ways. Let's say the simplest engineering approach is sampling points, right? And then the more, and let's say this black box method is using mathematical quantifier elimination, but maybe we don't really understand what's happening. And then, you know, if we want to be algebraists, then maybe we take this approach using Macaulay 2 and computing the boundaries and using like behind it the implicit function theorem. Okay, so let me stop sharing. So now we can put the screen up.
Are you done with that?
I'm done. So now it will be on the blackboards.
Share screen.
Just close the share.
I will do it.
And so what we are going to talk about in the rest of the lecture, so basically what we end the lecture with is that it wasn't a surprise, let's say, that the boundaries are polynomials. So maybe it's not surprising anyway, but this is a highly non-trivial result in real algebraic geometry. And so basically today is, let's say, a reminder of very basic algebraic geometry and then introduction to real algebraic geometry.
So these things cannot be done without Maple or some software.
Well, you can, if you're very good, you know, by hand, you can construct definitely Jacobian by hand.
Yes.
You can find the minors by hand. Elimination, okay, you can theoretically do by hand, because what's in elimination, you take lexicographic monomial order, you construct the Krögner basis, but this means you would have to compute this. So let's say theoretically, yes, if you know all the algorithms behind everything, but maybe you don't want to do it by hand. I think
if one would like to use the Krögner basis stuff, so how should we proceed? X minus the first polynomial, then Y minus the second one, and then
exactly, and then computing the Jacobian of this. And then in this case, the Jacobian is 2x2 matrix, I think. So in this case, I think we can actually do this example because I haven't done this particular example, let's say, in the last 4 years. And then I think it's finding the determinant of this one. And then putting the determinant together with the parametrization maps, and then eliminate. So we have 3 polynomials, and then eliminating U and V. So, and although we don't compute the Krögner basis, then elimination behind the scenes, let's say we just use built-in, it computes the Krögner basis, because you need like you need kernel basis for an elimination order, and then you keep only these elements of the kernel basis that are only in the variables that you're interested in.
When we are doing the Grosvenor basis, so we have to include the third variable too. C is equal to.
In this case, there is no C. So in the example that I showed, there was one more variable. So in this case, it would be 4 variables: U, V, X, and Y.
Okay.
But so maybe I wasn't thinking about it, but maybe it's very instructive if we do this example during the tutorial session, so that we really do define these polynomials P and Q and see how to do it in practice, because maybe it's useful to know. And yeah, so these pictures that I was showing, this is from a paper together with Bernd Sturmfels and Pablo Barilla called "How to Flatten a Soccer Ball." So from 4 or 5 years ago. Okay, so now I'm sorry because I'm going to bore some of you, but just want to make sure that everyone's on the same page before we get to the semi-algebraic sets. And because we will talk about boundaries, so we really need to be clear about Zariski closure. So let R be the polynomial ring. So K is a field, and it will be Q, R, or C. And actually, let's say tomorrow it will be only the field of real numbers. Okay, so let T be any set of polynomials in R. And their set of zeros is called the variety of T. And actually it's affine variety, but I will, because we won't talk about any other varieties, I will just talk about variety. And it is denoted so it's all the points P and Kn such that f of P is 0 for all f in T. Okay. And I've already heard that many of you have taken algebraic geometry following Kubjas, so all of you are familiar with this definition and a couple of more definitions. But this is really a reminder. And let's do a very simple example. So if our T, so let's take K to be the field of real numbers, and T just y minus x squared, then we have T. So can anyone tell me what's the variety in this case?
On the real line, on the real thing, y is equal to.
Yeah, so it's the parabola y equals x squared. And then this is even simpler. So going back to abstract algebra. So the ideal generated by T and denoted the following way is the smallest ideal in R containing T. and R is the polynomial ring. And if you have taken algebraic geometry course, then you know that the variety defined by T is equal to the variety defined by the ideal generated by T. Okay, so that was first definition. Sorry, there are a couple of more reminders. And a subset X of Kn is a variety if X is the variety for some set T. And now a question to the audience. Can we assume that T is a finite set? And why? Sorry, can you say?
We are in a Nonnegative ring, so we can suppose that.
Yeah, so it's by Hilbert basis theorem, we can actually assume that T is a finite set. For if we consider polynomial rings over Noetherian rings, but in particular fields. And the next definition is the reason why I'm recalling you these definitions and why I didn't go directly to, let's say, semi-algebraic sets. It's because we are going to talk about boundaries. And when we talk about boundaries, we actually talk about Zariski closures. So this is related to what I've been talking about. So the Zariski topology. So we define the Zariski topology on Kn by taking closed sets to be the varieties. And note that I will do an example in a moment, but this topology depends on Kn. So I will do an example showing what I mean by this. And a definition that we need later. That's a risky closure of a set X is the smallest variety containing X. Let's do an example. So let's take our field to be the field of rational numbers. Then this set plus square root 2 and minus square root 2 is a variety. In K, but we just take plus square root 2, the set consisting of plus square root 2. This is not a variety. And in fact, it's a risky closure of Y is X. Because the minimal polynomial of square root 2 over Q is X squared minus 2.
Rational or irrational?
Sorry?
Scaling to
Is irrational number.
So when we are talking about the underlying affine space, so this is going to be Q.
Yes, sorry, here K. If we would consider, and this is what I meant here, the topology depends on the choice of K. If we take K equal to the to R, then Y becomes a variety. Right? Because we can just take the polynomial X minus square root 2. But this is not a polynomial in the polynomial ring over Q. So there is really this difference in the topology depending what is K.
X is a variety in Q.
So the point scalar Q is not in Q, right?
Oh, sorry. Yes. You're completely right. So I'm mixing things up. What I was, sorry, ignore this example. So I guess what I was thinking about here from where if you consider polynomials with coefficients in Q and but we leave ourselves in R. So sorry, this is completely ignore this. I'm sorry about this. Well, it's still true that Y is a.
we can change the field Q scalar to, then probably you are right. Yeah, the risky layer of Y, then it's going to be S.
Okay.
Quadratic field Q scalar to.
Q Yeah.
लेकिन जब उसका वो गुजारिश की पीरियड जब y का नहीं
You know,
पहली स्क्वायर रूट टू तो पहली इसमें तो वो तो
let's forget this example. So I took this example and I didn't think about it. So actually it's the paper that we wrote on non-negative rank with Bernd Sturmfels and Elina Ropava. And there we considered the setting where we changed the coefficients of the polynomial rings. But then we considered the variety always like in Rn, Rcn, and then it makes sense, but it doesn't make sense the way how I introduce things here. So this is where the mistake comes from. So you're all completely right. So let me erase this. So yeah, sorry about this.
Strong theorem scalar going back to the radical. Strong.
Okay, so let me write down the last definition that I have about, let's say, classical algebraic geometry, and then we go over definitions in real algebraic geometry. So, given any subset X in Kn, we define the ideal of X by, so it's all the polynomials that vanish on all the points of our set X. It's all the f in R such that f of p is equal to 0 for all p in X. And the Zariski closure that we just defined and we'll denote Zariski closure by X bar equals the variety of the ideal of X. Okay, so now we go on with real algebraic geometry, and you're familiar that most of the time in, let's say, classical algebraic geometry, we work over algebraically closed fields. So many results don't necessarily, like Rulstellen sets that don't hold, or at least some of them don't hold over not algebraically closed fields. But in real algebraic geometry, it's very important that we have an ordered field so that we can compare the elements. So, and in real algebraic geometry, we allow inequalities in addition to equalities. So a basic semi-algebraic set X, which is a subset of R to the n, and here we always have R to the n, so we don't consider any other fields, is a subset of the form X, that's all the points in Rn such that f of p is 0 for all f in T, where T is a finite subset of R, so the polynomial ring in n variables over R, and G of P is greater or equal than 0 for all G in S, so where S and T are finite subsets of R. So this is a basic semi-algebraic set. So this is a building block for general semi-algebraic sets.
Is it necessary that S and T need to be finite?
I think yes. I can't give you. I'm pretty sure it's necessary. I can't right now come up with an example on spot where where we would have infinitely many, and we would get like something that's not that we don't want. And then a semi-algebraic set is obtained from basic semi-algebraic sets by taking by a finite sequence of taking unions, intersections, and complements.
So the rational is not a semi-algebraic set, right?
Sorry?
Set of all rational numbers is a semi-algebraic set.
It's not a semi-algebraic set. Yeah.
So that's
Yeah. That's a good example. So it's a subset of Rn that is obtained by a finite sequence of unions, intersections, and complements of basic semi-algebraic sets. And I will do an example in a moment. And I also want to warn you that, like, in different references, this could be strict inequality instead for a basic semi-algebraic set. So, and this could be, let's say, closed basic semi-algebraic set. But for a semi-algebraic set, it doesn't really matter, because when we take complements, then we can get like from non-strict inequalities, strict inequalities. But and also one more thing. An intersection of basic semi-algebraic sets is actually always a basic semi-algebraic set. Okay, then we just add the inequalities. Okay, so but example. So if you consider the non-negative orthant So X is defined by all the points X and Y in R2, such that X is greater or equal than 0 and Y is greater or equal than 0. So this is a basic semi-algebraic set. Right? So it's of the form that I wrote over here. And actually we have no equalities, so T is empty set and S consists of two polynomials. And maybe more interesting, if you consider all but the negative orthant, this is a semi-algebraic set, but not a basic semi-algebraic set. Okay. So this is all the points Y. And usually it's not very easy to show that something is not basic semi-algebraic. Like with this non-negative rank, like the semi-algebraic sets that we are going to see, like we believe that they're not basic semi-algebraic, but you know, we don't really know how to show it. But in this case, probably one would consider again boundaries and see, you know, the boundaries would have to contain the Zariski closure boundaries would have to contain this line, and then somehow argue that one, you know, one can't get a basic semi-algebraic set using these boundaries. So not a basic semi-algebraic set. And now we get to the theorem that I wanted to get at the beginning of this lecture. In the first example, what is T is empty set.
Oh, T.
Yeah, actually also. S consists of so S and T are subsets of R. That's the polynomial ring in this case in two variables with coefficients in R. So maybe let me recall this. So and in this case, is it clear? What are the basic, like how to write it, let's say, in terms of the basic semi-algebraic sets? Right? It's the union. So the union of X and Y such that X is equal to 0 and X and Y such that Y is greater or equal than 0. So OR corresponds to uniqueness.
All algebraic sets need not to be semi-algebraic, or I think they are.
All, if you consider in R n, then every set is semi-algebraic, because then you just take the S to be empty set. Yeah. So you get a larger class of sets. Now, theorem, also known as Tarski-Seidenberg. So the image of a semi-algebraic set of polynomial map is semi-algebraic.
By map, you mean regular map?
Yes, so just every coefficient or like every component of the map is a polynomial map. Yes. And a question to the audience. If I replace everywhere here a semi-algebraic set by a variety, is the statement still true?
No.
No? And why not?
Contains a dense open set exclusion image.
Yeah,
But
so
that's a non-trivial thing.
So this is at least the example that I know the best. So if you consider the hyperbola, that's a variety of x times y minus 1. And if you consider the projection,
Yes.
right, to the x coordinate, then you get everything but 1 point, right? And this is not an alpha variety. But of course, it is true that the image of an algebraic variety under a polynomial map is a semi-algebraic set. So this is a semi-algebraic set, but it's not an algebraic variety. Okay, and as a last thing today, I want to give you the definitions. What's the reason why we been defining everything, and what we will use then tomorrow. And that's connected with the motivating questions that I asked in the beginning. So let X be a semi-algebraic set. A point C is an interior point of X if there is an open pole such that if you consider the Zariski closure of X intersected with the open pole, that this is contained in X. And here the Zariski closure is necessary because we could have something that's defined by equalities and inequalities. Okay. We call a point P in X, a boundary point of X is not an interior point. And the set of all such points is called the topological boundary of X. It is denoted by and then finally, the algebraic boundary is the Zariski closure of the topological boundary. And recall that we noted the Zariski closure by bar.
Partial X instead of partial P.
Sorry. Yes. Thank you. And maybe let's quickly do an example, very simple example. If you consider this semi-algebraic set, what is the algebraic boundary of this semi-algebraic set? Let's say this is the x-axis, this is the y-axis, and let's say this is the point 1, 0, and 0, 1. Say again.
Boundary line axis.
Exactly. It's the topological boundary using the definition that I gave. Sorry, I should come out of time. So this is the topological boundary. It's just the boundary of the triangle, and the algebraic boundary is the Zariski closure of this. So the smallest affine variety containing the topological boundary. So it's the extension of this 3 line segments. So the algebraic boundary is the union of 3 lines, and it's defined in this case by this polynomial. Okay, so I will stop here. We are out of time. I will prepare the computation for the motivating question for the tutorial, and then tomorrow is the finale of like everything that we have discussed, combining all the lectures. Thank you very much.
Thank you. Are there any question in the chat box? Yeah. So, okay, you mean R deletion is 0 is semi-algebraic, but not a variety? She didn't say that.
Yes, it was related to this example over here. That the projection of the hyperbola is R minus 0. So, and I'm claiming this is not an affine variety, but it is a semi-algebraic set.
It's a semi-algebraic set. Okay.
Yeah, and maybe, yeah, and it's not the basic semi-algebraic set, I believe, and it's a union of complements of two basic semi-algebraic sets.
Yeah, okay, okay. Are there any other questions from the audience?
Just a source for a good proof of Tarski's Heisenberg theorem. I know it's very classical, but is there in some modern book you recommend some?
So my group just worked through the proof, and but I forgot what was the book. I think the classical, let's say, real algebraic book is by Roy. Exactly, but they actually found a different book, and I forgot the reference, and I think maybe, but I can ask it by tomorrow, and you know, I think they found the proofs there like easier to follow. Yeah, I have to admit I have not worked through the proof myself. It's not trivial.
I know.
Just curious about this semi-algebraic structure. So particularly this particular setup is for any field, or does you really require the field to be algebraically closed?
No, ordered
field, because we have inequalities. So if you would have complex numbers, inequalities wouldn't make sense.
Okay.
But I have to say I have worked with semi-algebraic sets only over R. But, you know, you need something where the inequalities make sense.
Any other question from the audience? Like, just curious, one more question. Yeah, in the order field, so it will not include the case of finite fields.
Yeah.
Any other question from the audience? Okay, if this is the case, let us, yeah.
Again, I'm not new stuff to me. I'm not an engineer. I'm not from algebraic geometry. But I just want to understand that we have an optimization, a similar concept of interior points and boundary points that appear, and the definition is exactly like that. So I'm just trying to understand as a layman perspective that I understand what the topological boundary is, and that example that you showed, it's basically the periphery or the perimeter of the region. So what do we gain as a layman perspective by getting the algebraic boundary and Zariski closure that you were saying with extent? So what are we trying to gain in layman terms here?
So the reason why we define it, of course, we would, the most interested we are in giving the semi-algebraic description. And you know, next best thing is the topological boundary. But the thing is, we want something that we can approach with algebraic tools. And for example, what I showed you this example in the beginning with the image of a unit pole, like I wouldn't know, like let's say, probably once we have computed the algebraic boundary, we can come up with the topological boundary. But let's say for me, this is the very first step towards, it's just like a tool, you know, towards maybe what we really want to get. So I'm just saying it's more difficult usually to describe the topological boundary than the algebraic boundary, and it's even more difficult to describe the semi-algebraic set than the topological boundary.
And am I right in saying in that example, so basically you have 3 hyperplanes?
Yes.
And the intersection is basically the topological boundary.
Not the intersection.
Sorry.
The intersection would be 3 points.
It's a region. It's a region of interest.
Exactly. Exactly. But that's also not always true. If you think back about the first example that we had, then the algebraic boundary intersects the region in the interior. Remember that there was this folding.
I actually came a bit late, so I'm sorry.
Oh, you came late. Okay. So, but I can show you a picture. But even this is not true in general. That the topological boundary is the intersection. It's contained in the intersection of the algebraic boundary and the region we are interested in.
Okay. And just one again, because this is not my field, just wondering. So let's say that instead of having this kind of a region, we had a circular region. Now I know that on every point on the circle, I have a tangent hyperplane. So I can describe that these are algebraic objects. So will that actually be, so all the collection of those tangent hyperplanes, will that be something similar to? And so those are all affine?
So in the circle case, actually the algebraic boundary is just the boundary of the circle. It's because this already is the x squared plus y squared minus 1. So it's so in this case, the algebraic boundary coincides with the topological boundary. So you know, all things can happen basically.
In the circle with the tangent lines, that would be a cylinder.
Yeah, no, like for example, if if I have to prove convexity of this region, so it's basically an intersection of hyperplanes. Hyperplanes are affine and convex, so intersection is convex. So a norm ball is convex. You can prove through simple like those convex from first principles, but you can also prove that it is an intersection of hyperplanes, supporting hyperplanes, and that region is also convex. So you can actually trace the boundary of a circle by just moving the hyperplane, algebraic hyperplane, like a circular motion. That you can do that. But again, I'm not familiar with algebraic geometry, so I'm just trying to relate those things.
And this is, you know, all these supporting hyperplanes, they define the unit ball, but it's not a semi-algebraic description because there are infinitely many of you need infinitely many supporting hyperplanes. But in this case, yes, the algebraic boundary is x squared plus y squared, like defined by x squared plus y squared minus 1. So it's really different things can happen. Yeah.
Any question from the IBA side? IBA Karachi? Any question? Numana?
No question.
No question. Okay. If this is the case, let's thank Kaie for her second lecture, second last lecture. There is an announcement.